Okay, well, we know that the expected value of the sum of variables is the sum of the expected values. Is that true of the variance? Well, it turns out not in general, but if the variables are independent, it's true. So we want to show that now. If the variables are independent, I expect this to evaluate to the sum of the variances of xi. Otherwise, it's not necessarily going to be right. So first, I will use the property 2 the other way. So often I want to use it right to left. So I'm going to say this is covariance of 1 to n xi, and I'm going to use different, I'll still be 1 to n over here, but it should be xj over here, just so I don't get confused with those. So I have the same sum on both. I'm using the j index on one and the I on the other. So that is basically true, right? That's true. It's just going right to left. And now I'll use property 4, that it's just the double sum of this. So I equal 1 to n, and j equal 1 to m, covariance xi xj. And what we get is how many n times m terms? Yep. But oh yeah, m is the same here. So this is just n. I had it right here, but this should be n. Yes, we get n squared terms, right? Because it's the sum. I'm taking it with itself. Now, what happens? I have n of the terms are the same. I equals j n times. And the other times they're not equal, and I might get like covariance of x1 and x3, but then I'd also have covariance x3 and x1. By the reflexive property 1, those are the same thing. So I get doubles of all the ones where they're not the same. So this is equal to sum. I can group the first ones all in the same. I equals 1 to n, covariance xi xi when they're the same. And now I have plus all the ones when they're different, and I can make that into 2 and take a double sum, have I less than j less than n here, and covariance xi xj. This will be n times n minus 1 terms, I believe. N choices for the first, and minus 1 for the second. Yes, yes. Yes, that's true. And then times 2. So this is right. This is right. Okay. All right. So this is n terms here. And how many terms are here? This would be n total, counting the 2, n times n minus 1. One way to think about it is the pairs here are n choose 2. That's how many there are. But then I'm multiplying by 2. So it's really n permute 2 is the total number here. So it adds to n squared when I add these up. So when I add these up, I get equals n squared. All right, but anyway, this is just, the first one is just the sum. I equal 1 to n, and this is also known as the variance of xi. Now here, though, this is independence. So if they're independent, it's 0. So I have plus this extra term. 2. Okay, but if xi's are pairwise independent, as in trials of a binomial experiment or something like that, then all the covariances terms, then all the covariance xi xj are equal to. So right, when the xi's are independent, or just pairwise independent. Okay, that's a big result. Example. If x is binomial, say NP, then we can write x equal to a sum where the xi's are IID, independent, identically distributed Bernoulli P. Well, I know the variance of xi, Bernoulli P, P1 minus P. So the variance of x is equal to P1 minus P by independence. I can just sum. Okay. All right. For example, suppose x is binomial 100 and 0.8. Then variance of x equals 100, 0.8, 0.2. So that's, what the hell is that? That's 0.16 times 100, so I get 16. Also remember then the standard deviation of x equal to the positive square root. Variance of x would be equal to 4 in this case. Yes, I suppose that's right. Okay, let's see. Let's stop this one now. Continue on the other side. Yes.